Welcome back to the classroom. My name is Mr. Wong. Today we're going to be covering Module 3, Waves and Thermodynamics, Inquiry Question 5, Thermodynamics, and we're going to explain the concept of thermal equilibrium. So let's go. Before we start, let's just talk about how thermodynamics works. Thermo, meaning by heat. Dynamics represents, the system in which it's happening. So what we mean by thermodynamics, we're looking at the behavior of heat transfer, the way that heat works. And there's a couple of things you need to take into account when we talk about thermodynamics. One, we are always following the law of conservation of energy, the notion that energy can't be created nor destroyed, but simply transferred or transformed. Now, imagine the best example of law of conservation of energy is imagining you're cycling up a hill and then you're cycling down a hill. When you're cycling up a hill, you're using energy to make you move from one position to another. So that moving motion is kinetic energy. As you move closer and closer to the top of the mountain and then reach the top of the mountain, you have potential energy. So the potential energy here comes from the ability of gravity pulling you as the cyclist back down to the bottom of the mountain or the hilltop. So that's a conversion. That's kinetic energy converting into potential energy. And once you reach the top and then you start sliding down, you go from zero motion to a lot of motion, and that potential energy is then being transformed into kinetic energy. Notice energy isn't being created or destroyed here, it's simply transferred from one end to another. If we look at the whole equation together, we can call this the internal energy, or we can say from module 2, we gave it another fancy name, we called it the mechanical energy. Okay, so mechanical energy. And it basically says the total energy of the system would equal to 0. Okay, so that's what we meant. All right, let's firstly talk about heat transfer, and let's also look at the concept of thermal equilibrium. We talked about in the previous video, the ability to sense heat or cold is to do with how well heat is transferred from one particular component to another component. So imagine you have 3 tubs of water. One is really hot, one is really cold, and then one that is just, average room temperature. In the hot water, you'd feel obviously really hot. In the cold water, you feel really cold because heat is being taken away from your hands. In the hot water example, heat energy is being transferred into your hands. Now, say if you put both your hands into the room temperature water after that, what would happen? Well, for the hand that was in the hot water, you'd feel a lot colder because the heat energy in your hand is now being transferred into the tub of water. For the cold hand, putting it in a warmer temperature of water would mean that the heat or the kinetic energy of the water is transferred back into the hand that was in the original cold water. Okay, so let's talk about the concept of thermal equilibrium. Okay, now equilibrium means everything is balanced. Thermal means heat, right? So when we mean thermal equilibrium, we mean that the heat is equally transferred on both sides. So let's just quickly define thermal equilibrium. So the rate of heat transfer is equal between the objects. So the best way of knowing if we've reached equilibrium in terms of heat is temperature, right? If we have the same temperature of 2 objects in direct contact with each other, we know we've reached thermal equilibrium. Okay, so thermoequilibrium occurs when there is no flow of energy between the two objects. They approach the same temperature. Or you could say the transfer of energy is at equal rates to each other. The temperature is maintained unless it comes into contact with another object. So thermal equilibrium means both objects have the same temperature. Something will not be in thermal equilibrium if it's still transferring from one object to another. This is actually an example of the zeroth law of thermodynamics. Why do we have a zeroth law? I don't actually know the context, but we do, so we'll live with that. The zeroth law of thermodynamics states if you have two objects in thermal equilibrium with a third object, then they are also in the thermal equilibrium with each other. So that's a lot of different words. Let's just kind of explain that. Let's say object A, object B. They are blocked off by an insulator, so they're not going to have any heat transfer between each other. But what we do know is that object C is at 25 degrees and it's transferred its thermal heat to object B, and it also has 25 degrees. So the assumption we can make is that if A is also connected to object C, it must have the same temperature as object B, which is 25 degrees Celsius. So that's what we're looking at here as the zeroth law of thermodynamics. Okay, so that's kind of explain the two things. Two systems in thermal equilibrium if and only if they have the same temperature. Keep that in mind. When it comes to an application of the zeroth law of thermodynamics, think about a goldfish. For those who have used to have a goldfish or do have a goldfish as a pet, we cause the water in the bag to reach thermal equilibrium with the temperature of the water that's in the fish tank. Now, obviously, as you know, it's not an instantaneous process. It does take time for heat to be transferred from one end to another. Now, this is good for, goldfish because that is a gradual decrease in temperature or gradual increase in temperature depending on the water you're using, and allows it to survive. If there is a sudden drop in temperature, then the goldfish will die. Okay, so you allow for enough time, you allow for thermal equilibrium to be made between the two water sources. Let's look at the first law of thermodynamics. Now that we've talked about what thermal equilibrium stands for. So the first law of thermodynamics, my apologies, is this exact same thing as the law of conservation of energy. So energy cannot be created nor destroyed. Any energy changes in a system must be accounted for. Okay, so as a reference point, if we put energy into the system, it must have gone into the system, or it must have been work to make the system do something. Okay, so we have this nice little formula here. Okay, so imagine a balloon is heated by the sun. Okay, this supplied heat causes an expansion of the balloon as the air does work to push the balloon outwards. Okay, so this is the formula we're using. Delta U is the change in internal energy. So internal energy meaning by the reaction vessel. Capital Q represents the heat energy of the system. And then W represents work. Now, we write this as negative work because it's work done by the air, while this Q is heat applied to the air. Okay, so we have the concept of energy that goes into the system and energy that's coming out of the system. So perspective is quite important. So let's kind of delve into how we differentiate between the two. Any change in internal energy, it could either be potential or kinetic, is equal to the change in heat energy. So whatever the properties of the internal energy, that's changed by the heat energy. And we write the formula like so. if we have the system absorb heat, so energy is going into the action, Q is a positive value, so heat enters the system. If a system releases energy, so the reaction vessel, you could say, gets colder, or sorry, not colder, but like hotter actually. So when it releases that heat, Q would be a negative value. Negative being that heat is being released into the environment. If a system does work, so let's say the air particles expand the balloon, then the work we do is a positive value. If the surrounding does the work in the system, so pumping a tire, that is the work would be a negative value. Okay, so we're talking about what's inside, what's outside of this particular system here. Let's use some examples that might give you a better understanding between them specifically. So let's go through our example here. Now, in this case here, we have 25 kilojoules of work done on the system. So the surrounding is applying the work onto the system. So the work done here is a negative value, negative 25 kilojoules. The surroundings, or the system itself, loses 30 kilojoules of energy into the surroundings. Okay, so that is a negative value. So the overall change in the energy in the water is negative 30 kilojoules, subtracted by negative 25 kilojoules of energy being done onto the system. So overall, two negatives make a positive. We have negative 5 kilojoules of change overall in the energy of the water. Alright, so let's have a read of question 2. A student places a heating element and a paddle wheel apparatus in an insulated container of water. She calculates that the heater transfers 2,530 joules of thermal energy to the water, and the paddle does 240 joules of work on the water. Okay, so for this one it says calculate the change in the internal energy of the water. So the water here, according to this question, the water is our system. The paddle wheel is the surrounding. So delta U is equal to the energy. The energy right now is being transferred to our system, so it's a positive 2,530 joules, subtracted by 240 joules. This is going to be a negative value because it's the surrounding that's applying that energy onto our paddle. Okay, so that's what we have there. So the final answer we get in this scenario is a change of 2,770 joules of energy. Okay, we'll go through one more. We have a balloon that's placed in direct sunlight. The sunlight supplies 200 joules of energy to the balloon. The air pushes out the balloon surface, doing 50 joules of work. How much does the internal energy of the balloon, or the air inside, change? Okay, so energy is being transferred into the balloon, so that means that we have a positive 200 joules of energy. 50 joules of work is being done by the air inside the balloon to push out, so that means we have a positive value because work is being done by the system we're looking into. So we have a overall change in 150 joules of energy. Question 4, while doing some heavy lifting, you do 2,500 joules of work on the weights while releasing 3,000 joules of heat. Okay, how much energy did your internal energy change? So the internal energy, you released 3,000 joules, so you are 3,000 joules less than before. You are doing 2,500 joules of work on the weight. Now, this is the amount of energy we're talking about that's in U. Okay, so if you are doing that work on the weight, then that's positive 2,500 joules of energy. Okay, so what we have here is an overall net of negative 5,500 joules of energy, of internal energy change. Okay, so there you go. Right, so that concludes our lesson for today. Hopefully it gives you a better understanding of what we're talking about. Hopefully this explains now what thermal equilibrium is, and also a couple of the laws of thermodynamics. In the next section, we're going to start calculating how heat transfer works. So we talked about how I'll say that again. So we'll talk about what heat transfer is, and we'll also quantitatively, so numerically, demonstrate how much heat is transferred based on the material it's in, and what are the implications, what are the effects of all that. So hopefully you enjoyed this video. I'll see you next time in another series about physics.